Hello, everybody. Let's look at a paper on neural network and the genetic optimization and the application to power plant optimization. So here, the title is Smartsheet tool applied to performance analysis and economic optimization of a CFB boiler. I'm going to explain what a CFB boiler is. So IPCC 2010 refers to International Pittsburgh Coal Conference in 2010. It was hosted in Turkey instead of Pittsburgh. So the presenting author was Panos. He's a CFB expert of Alstom Power and later GE Power. And this Avinay Ajashi is a control engineer. And this is me. I serve as a project leader and controls team leader. And this Kanu Schaefer is my department manager. And Wiko Verta is the superintendent, is basically plant manager for a power plant in Connecticut. So the electric power company is called AES, is a global electrical power company. So again, this International Pittsburgh Coal Conference was held in Istanbul, Turkey in 2010. So let's look at the outline. So we got 7 items here. Item 1, we're going to introduce the Smartsheet concept. What is a Smartsheet? And topic 2, we talk about the neural network model we use in this work. And topic 3, we talk about the economic optimization specifically for this power plant. And topic 4, we talk about the boiler test and the resulting data we collected from the power plant. And topic 5, we talk about the model development results using the neural network training. And topic 6, we're going to look at the optimization results together. We look at this a couple of optimization scenarios. And then we summarize the work. And here is the view of a typical CFB boiler. This is a CFB boiler for this power plant. AES Thames is a power plant located on the bank of Thames River in Connecticut. So there are 2 CFB boilers and one steam turbine and a generator. So it supplies power to the grid and also supply steam to the local industrial plants. And here is the general arrangement of the boiler. And Smartsheet, what is Smartsheet? It's basically Excel-based optimization tool. So it's offline, but with neural network embedded. And also you got optimization engine built into the Excel. And then when engineers use the Excel spreadsheet, you can do offline optimization using different scenarios you design with your team. So this is how the Smartsheet looks. So we even try to put a name called Smartsheet and TM as the trademark. So basically, it's a Smartsheet, and then we have all the variables that will help us optimize all these output variables. So performance variables. And here we can navigate. There's a control panel here, which allow us to navigate through different functions as a model, as basically your model structure, the inputs, the data you can put here, and you can generate the calculations as output, and you can change or added to the economic cost that we do, and then sensitivity analysis and sensitivity results would be displayed in this worksheet, and there's optimization results, and we can examine how much improvement is done, and you click here to calculate improvement, and it will get the results here, and then you got the final report. So here these variables, we look at that. Primary airflow, overall oxygen level, secondary air pressure, lower bed temperature, combustor differential pressure, percentage of a coal. B, mean we have three coal lines, A, B, C, so we look at percentage of a coal line B and the percentage of limestone B, and ambient temperature, and flash reinjection on and off is binary decision variable, and we have megawatt net demand, and we have PS flow, and then we look at what is neural network. Here is the structure of the neural network. We have all the variables we just walk through. Plus, there's a decision variable, we call manipulate variables. And we have three disturbance variables that these variables we can measure, but we cannot control. Like ambient temperature is the temperature you have. Is the weather for today, but you cannot really control that. And megawatt demand is from the dispatch center. So and there's a process steam flow because that's the demand from the industrial plant. How much steam they're gonna request is unpredictable, is to the power plant itself. So, but there's a range. There's a range. So, but the specific number is not predictive. So we count it as disturbance variable. It means we can measure, but we cannot control that. And here is the neural network. Basically, it's the three-layer neural network: input, hidden layer, input layer, hidden layer, output layer. So, and then we have the cold feed. Means we'll predict what is cold feed for the given megawatt number, megawatt demand, and how much NOx is generated, how much limestone is used. We've got three outputs for this neural network. So what do we try to optimize? So like economic optimization is based on a neural network nonlinear model of this CFB boiler, and the minimization of the operating costs, including total fuel, limestone, NOx credit, and ash disposal. So fuel is easy to understand. You're going to burn a fuel to generate heat, and limestone is used to capture SO2. So that's a cost. Limestone material and the processing, energy, and labor. That's that at the cost. And NOx is anything beyond the standard will be counted as either positive or negative NOx credit, and where you can it will trade internally within AES. So, and there's ash disposal. There's cost for disposing the ash. So from the bottom of the CFB boiler, you're gonna collect the ash, but you need to dispose that, and dispose the cash is the cost. And the optimization function is the linear function equation. By adding all these together, the weighted average now is a weighted sum. So overall, optimization problem is nonlinear and can have multiple local minima. So the overall optimization problem is considered nonlinear. Is not a simple linear problem. And optimization problem solved by global optimization technique. We use genetic algorithm. So it's one of the typical stochastic optimization method. So topic 4, boiler testing. So how we actually did the test in the power plant. So test was conducted on the CFB Thames and on one of the boiler. Tests were conducted to collect data for neural network training. So in total, 18 orthogonal test conditions based on the principle of design experiment (DOE). So it's not Department of Energy. It's design of experiment. So DOE test metrics with 18 orthogonal test conditions. So each manipulable is changed to 3 different levels, and each test condition run for 18 to 24 hours, and we try to maintain the same megawatt load condition. The complete set of tests took about 1 month of normal operating time with the minimum interference. So it's a long time commitment, and thanks to WICO and the AES team, so sometimes they have to sacrifice the opportunity to capture the peak power price in order to finish this plant the design of experiment DOE tests. So here is an example of the test data. Is the PI flow. This is basically the number of points. It's representing the time, and is O2 level, section air pressure, and the low bed temperature. And the sampling rate is 5 minutes is average. So we look at this is neural network is basically a steady state performance model. So this one is CV, this one is the MVs, multiple variables, the input to the neural network, and CVs are the output variables of the neural network. So there's a fuel, there's a limestone, and a NOx. So, and with the model structure, with the input, the output, we get the data to train the model. See, we got the model structure, and we have the input, 11 inputs, the 8 manipulable plus 3 disturbance variables, which gives prediction of coal, feed, NOx, and limestone. And we use the measurement data as for supervised learning and to get the model trained. So, and then we're gonna check the prediction, how that really works. So they follow that pretty well. It's not 100% follow, because in neural network training, make sure you don't want to follow that 100%. And this model basically also filter the noise. See that actual is this. So, and the black is the predicted. Predicted basically act as a filtering a function as well. So, and then when we have the model, one important thing is it's not just predicted accurately. We also want to check the input-output relationship are right, reasonable. So we do the sensitivity analysis. Means we give range of change on the input and the calculate output, and we draw the trend. So for example, bed temperature change from this level to this level, and what is the boiler NOx level? So, and we want to evaluate if this trend is right, at least it's quantitatively right. So bed temperature go up, NOx will go up. So using our engineering common sense, this is right at least. And the low bed temperature goes up, a few total is going down, and it is opening point, and beyond this point will go up again. It's this kind of reasonable, and the engineering expert kind of agree with that. Low temperature bed temperature is keep it going up. As temperature going up, limestone will consume more. So the best temperature for SO2 capture for CFB is between 850 to 900 degrees Celsius. And as temperature keep going up, and the efficiency will drop, and the limestone total consumption will go up. So this one is talking about the PA flow. Say if the PA goes up, and boiler NOx will go up. And this one also draw the curve at different overall O2 level. So the trend is the same regardless of the O2 level, but as O2 level go up, the go up, so the NOx will go down in this case. So this yeah. So this O2 equals 3, and this is O2 equals 2. So if O2 goes up from 2% to 3%, and NOx will go up. And this is the optimization result. When we have the model, we already defined the optimization function, and we can do the potential cost reduction calculation. It's 2%. So we do estimation. So this is the actual. This is how much room we can have for improvement. So basically, we predict that there's 0.02%. It's pretty minor as itemized cost, but this one is 1.4%. Item cost is 0.76%, and limestone absolute value is 30%, 3% improvement. That's a lot. And the itemized cost saving 0.67. So ash total is 9.1, and this is 0.05. So overall it's 2%. Itemized means they normalize as to the same criteria. So, and this is again, look at the optimization cost function is we put a different weight, the price, C1, C2, C3, and C4. C1 for fuel, C2 for NOx, C3 for limestone, C4 for ash disposal. And manipulator variable used they are these we already discussed. And a set of optimization solution ranked based on operator means this optimization, since it's offline, instead of giving a single optimization, we basically can select this as the best one, rank number 1. But in this tool, this give you kind of 10, give you 10 best numbers from the cost 15.71, 15.96, and let the engineer can evaluate that quickly. For example, these two kind of the cost is the same, but you look at the rest looks similar, but PI flow is low. From operation point of view, typically we're going to select the 2 instead of 1 because we're going to have use a lower PI flow, right? That's just an example. So also we're going to evaluate this one is even lower PI flow. If the operator want PI flow I want lower PI flow, then we'll probably select this one. So I can bear with the cost, but PI flow is lower. I use lower electrical power, and but asset pressure is pretty high, 58, and this operator can use, or engineer can use their common sense to evaluate the different operating scenarios. So give you 10 best cases, and you can give you a chance to evaluate before you apply it to the DCS. So optimization results can vary when there are changes in fuel, limestone, ash disposal prices, or NOx credit. So this one is so the cost is 15. Current price is 15.71 with this operating scenario. And when fuel price changes, and the unit will drive the unit to achieve minimum cost differently. See that when fuel prices drive up, so the units will operate differently. So that means to give more priority for fuel savings. So the PA flow goes up a little bit, and O2 is almost the same. We drop asset pressure, drop lower bed temperature, we keep DP set point same, we keep this same, but we drop limestone for B. So if limestone price goes 25, this operating parameters the software recommend. And if ash prices goes up by 25, and this have a set of parameters that the smart tool really advise us to use. So then as NOx price goes by 50%, and the potential results would be different. So operating cost above is a rough estimate. It does not reflect the actual generation cost. It's remind everybody is this example. Don't apply that to your power plant. So we don't have the liability when we present this to you. So to summarize, Excel-based boiler operation tool, which is named the Smartsheet, was developed using artificial neural network model to capture the boiler operating characteristics, and it features two types of boiler sensitivity analysis functions. That means a single input, single output, and the two input and the one output. So it's two types of boiler sensitive function you can evaluate. And we use economic optimization to generate minimum cost operating settings for the CFB boiler. Boiler optimization and Smartsheet validation tests conducted in the circulating fluidized bed. And we have done a series of optimization scenarios, and we tested this scenario with potential average savings of more than 2% operating costs. 2% is a lot. So future work, and we're going to do additional boiler tests that were planned to validate operation results. And the scope of the Smartsheet is planned to be expanded to other types of boiler. For example, later we expand the use of the Smartsheet to PC boiler. For example, for services engineers, we add this to the services engineer toolbox so that they can get the data and do quick estimate. So by doing what, we can improve the boiler efficiency, or improve the NOx emission, or we can reduce the limestone usage, or we can reduce the ash disposal costs, so as the consequence of fuel and limestone usage. So this is interesting work. So that's what's done in 2000 between 2008 and 2009 and 10. The paper was presented in 2010. Paul Panos, my colleague, went to Turkey to present this, and we list Wico as the author, and he agreed on that. Wico later moved to AES California, and in 2016, when I went to Newport for a conference, leader conference of ISA, I drove to his power plant to meet with him, and he was the plant manager for two power plants over there. But he said he's going to have a new job, assume a job as vice president of AES California. So that was 2016. So hope Waco's doing well in California, and hope we can meet in Connecticut when he comes back. I hope if you have any comments, so please add to the comments space below.